So, welcome to lecture series on advanced linear algebra. In my last lecture, I have introduced the concept of inner product for different vector spaces. To understand the concept or length of a vectors, let me introduce one more terminology called norm of a vector, please. Norm of a vector. What is that? Let V be a vector space over a field capital F. So, the field here either real number or complex number, please. Let alpha belongs to V be any element. Then the positive square root of inner product of alpha and alpha is called as norm of alpha. Mathematically or symbolically we used to denote as a norm of alpha as like this. This norm of alpha, it can be considered as the length of the vector alpha. Let me also define another terminology called quadratic form. Let V be a vector space over a field capital F. Quadratic form is a function which assign each vector alpha to square of the norm of alpha. This one, please. Now, using this terminology norm or quadratic form, we will see the characteristics of the inner product. We have if a norm of alpha plus beta whole square, if I consider this ones, this is equal to what? This is equal to, according to definitions, it is equal to inner product of alpha plus beta comma alpha plus beta. In fact, if I consider norm of alpha plus minus beta whole square, then I also have to consider minus here also. So, this is equal to, according to definition of the inner product, this will be equal to inner product of alpha and alpha plus minus beta plus minus beta and alpha plus minus beta, please. So, this is equal to, we will have this is equal to inner product of alpha, then plus minus, because the positive real numbers 1, I can take it out. So, plus minus inner product of alpha and beta, and then this one will have plus minus inner product of beta alpha and then plus minus into plus minus. So, it will be basically plus inner product of beta beta. Okay. So, using the axioms which what I have used in definition of the inner product, I can write down that norm of alpha plus minus beta whole square as inner product of alpha alpha plus minus inner product of alpha beta plus minus inner product of beta alpha plus inner product of beta beta. So, according to the definition of norm, this is equal to quadratic form of alpha, that is equal to norm of alpha square. Then plus minus inner product of alpha beta plus minus inner product of beta alpha and plus norm of beta square. We are having like this. But inner product of alpha beta and inner product of beta alpha is basically, I mean, if I consider z is a complex number, the z and z plus z bar. So, this will be equal to norm of alpha square plus minus 2 times real part of the inner product of alpha beta, because z plus z bar equal to 2 times of real part of z only, x plus iy plus x minus iy, it will cancel out basically 2x. So, that is why, okay, plus norm of beta square please. So, I am getting norm of alpha plus minus beta whole square, that is equal to something like this. So, we are getting norm of alpha plus beta whole square equal to norm of alpha square plus norm of beta square plus 2 times of real component of inner product of alpha beta, and whereas norm of alpha minus beta, that whole square equal to again norm of alpha square plus norm of beta square minus 2 times of real component of inner product of alpha beta. So, if I consider this is 1, this is 2. So, from 1 and 2 we have norm of alpha plus beta square plus norm of alpha minus beta square equal to 2 times of norm of alpha square plus norm of beta square. Just simply adding, I am getting this, but if I subtract 2 from 1, then we are getting norm of alpha plus beta whole square minus norm of alpha minus beta whole square. This is equal to how much? 4 times real component of inner product of alpha beta. So, this implies the real component of inner product of alpha beta equal to 1 by 4 norm of alpha plus beta whole square minus norm of alpha minus beta whole square. Okay. We also know inner product of alpha beta, this is equal to real part of inner product of alpha beta plus I times real part of alpha and I beta, because I times imaginary part of inner product of alpha beta, that is basically equal to real part of inner product of alpha I beta. Okay. So, we have like this. So, this implies real part of alpha I beta, that will be equal to, according to these definitions, if I consider this is star, then I will have real part of alpha I beta is equal to 1 by 4 alpha plus I beta whole square minus alpha minus I beta whole square, this one. So, finally, we see that inner product of alpha beta can be written as 1 by 4 alpha plus beta a whole square minus alpha minus beta a whole square plus I by 4 norm of alpha plus I beta whole square minus norm of alpha minus I beta a whole square, and this can be written in a compact form as a sigma n equal to 1 to 4. One can write I to the power n by 4 and norm of alpha plus I to the power n into beta whole square. Please check it. Okay. And this is called the polarization identity. This is called as polarization identity. Polarization identity, please. Okay. Okay. So, we have seen the relation between the inner product and norm or quadratic form also. Now, definitely we shall utilize this relation to understand the inner product more deeply. But before that, we have a one question. Suppose in a vector space V of dimension say n, that the finite number vector space is given to us, and suppose an order basis is given to us in that vector space, is it possible to express the inner product which define that vector space in terms of matrix? Let me consider like this. Let V be a finite dimensional vector space over the field capital F. Let this be an inner product, defined in V. It is given to us. Let B equal to alpha 1, alpha 2, alpha n be an order basis. Even if I do not give the order basis, if I stick to only first two lines, that V be a finite dimensional vector space over the field and an inner product is defined over the vector space V. My question is it possible to express the inner product in terms of matrix concept? So, answer is yes, it is possible, provided an order basis is given to us, please. Suppose an order basis of the V is given to us. So, in that case we will be able to express the inner product of the vector space V explicitly by a matrix. Okay. So, let me clarify this claim, please. So, let V be an order basis for vector space V. Let G k j equal to inner product of alpha j and alpha k, inner product of alpha j alpha k, because inner product is given to us. So, I shall utilize that given inner product to define a scalar G k j like this. Okay. So, now for different values of j and k, j varying from 1 to n, k varies from 1 to n, I will have a matrix capital G of n cross n order. I will show that the inner product what is given to us in the vector space V can be explicitly defined in terms of this matrix G, please. And this matrix will have some typical characteristics, that is it is Hermitians and invertibles. So, let us see all this thing please. So, star introduce says an matrix, an n cross n matrix G. Claim G is an invertible and Hermitian matrix. Let alpha belongs to V be any element, and beta also belongs to V, be also an element. Let alpha equal to sigma xi alpha I equal to 1 to n, and so that is coordinate matrix of alpha with respect to order basis B equal to capital X, which is equal to x1, x2, xn transpose, and let beta equal to sigma yj alpha j equal to 1 to n. That is coordinate matrix of beta with respect to order basis B equal to say capital Y, which is equal to y1, y2 and yn transpose please. So, now inner product of alpha beta will be equal to what? This will be equal to inner product of alpha equal to sigma xi alpha I equal to 1 to n, comma sigma yj alpha j equal to 1 to n. Not to confuse with the I as a square root of minus 1, this is I can rewrite this is equal to also sigma say x k alpha k equal to 1 to n, and this is your yj and alpha j equal to 1 to n, this one. Okay. So, this implies that inner product of alpha beta equal to sigma k equal to 1 to n yj alpha j equal to 1 to n. So, I can write down the inner product of alpha beta equal to like this. So, this is equal to again by the definition of the inner product I can write down this is equal to inner product of k equal to 1 to n, and then again j equal to 1 to n, sk will be there. So, xk and yj bar with their scalar quantity I will take it out, and then alpha k and alpha j inner product this one please. So, this is equal to sigma k equal to 1 to n, sigma j equal to 1 to n, x k and y j bar, and inner product of alpha k and alpha j. So, this is equal to, one can write down y star means y transpose and bar, conjugate transpose basically, and this is okay, this is, let me write down this one, this is equal to simply k equal to 1 to n, j equal to 1 to n, x k and y j bar, and this is equal to g this is equal to GJK, this is equal to GJK. So, this will give you basically Y star G matrix into capital X, because this is scalar quantity and dimension 1, and we can see by, if I consider Y equal to what I have considered here, Y is a column, the transpose means basically a row, then this multiplied the G is a n cross n matrix and X is a column, I will have basically dimension is a 1 cross 1 matrix, or this is scalar quantity please. So, we see inner product of alpha beta equal to Y star G X please. So, this implies inner product of alpha equal to X star G X, which is strictly greater than 0 for alpha not equal to 0. So, this implies G is positive definite, G is positive definite. Again G k j equal to inner product of alpha j alpha k, which is equal to inner product of alpha k and alpha j bar. So, this is equal to G j k bar. So, this implies G is Hermitian, G is Hermitian. Since X star G X is strictly greater than 0, I can say that G will be invertibles. Otherwise, there exists 0 not equal to capital X such that G x equal to 0, and then your X star G x, which is equal to 0, contradicts the hypothesis inner product of alpha alpha is strictly greater than 0 for alpha not equal to 0. So, therefore, G is invertible. So, we have seen G is invertible, G is Hermitian, and even the G I mean G j j, all the diagonal entry will be also positive quantity please, and G is also positive definite. So, we see that for a given inner product we are able to produce a matrix, n cross n matrix, invertible matrix, which is also Hermitian and positive definite matrix. Now, the question is, if an invertible Hermitian matrix which also positive definite is given to us, is it possible to introduce an inner product in this space? So, from this I can see, so given inner product we have an invertible Hermitian positive definite matrix G. Now, question is, if an invertible Hermitian positive definite matrix is given to us, then is it possible to introduce an inner product in this space V? Answer is yes. So, when an order base is given to us, then how to define that inner product? We will define the inner product like this. For a given G, you can define alpha j alpha k, inner product of alpha j and alpha k, that is equal to simply g k j. So, if I define this is the functions, then definitely these functions will introduce, then star will introduce an inner product in V. So, when this G is Hermitian, positive definite and invertible matrix is given to us, so in that case we can define the inner product in this space as like this. Now, we should utilize this concept to understand one nice problems, that is called Hilbert matrix. So, let me consider Hilbert matrix. Hilbert matrix is defined like this, say capital A equal to 1, 1 by 2, 1 by 3, 1 by n, 1 by 2, 1 by 3, 1 by n plus 1. This is 1 by n, 1 by n plus 1, it will continue 1 by 2n minus 1. Now, this is a standard n cross n Hilbert matrix. Now, this matrix immediately you see that it is symmetric matrix. See, what I have done it here, if the field complex number is replaced by real number, then I will have G as symmetry matrix instead of Hermitians. So, now question is, can I use this concept that G is has to be invertibles when G is basically coming from as a consequence of for a given inner product. Okay. So, now suppose A is like this matrix. So, it is also symmetry matrix. Is it possible to show that this matrix is also coming as a consequence of a given inner product on a given space, vector space? If it is, then immediately I can say A will be an invertible matrix space. So, now let us see what is that space and what is that inner product which will give this matrix space. Let V be the space of all polynomial functions of degree less than is equal to n minus 1. So, let B equal to the standard order basis in V, that is 1 x, x square and x to the power n minus 1. So, I have taken vector space of dimension n, accordingly I have chosen an order basis B equal to 1 x, x square and x to the power n minus 1. Now, consider an inner product okay. So, let me define inner product like this thing. For f and g belongs to V, inner product of f and g integration from 0 to 1 f of x and g of x dx please. So, let me define this one please. Let me consider inner product of x to the power j minus 1 and x to the power k minus 1. Let me consider inner product of this one please. Actually, I can give the name, this is equal to as f1, f2 and fn. So, fi equal to x to the power I minus 1. So, based on that I can write like this thing please. So, there is fk, fj and fk please. So, this is basically inner product of fj and fk equal to like this thing. This is equal to 0 to 1 x to the power j minus 1 and x to the power k minus 1 dx. So, this is equal to 0 to 1 x to the power j plus k minus 2 dx is equal to x to the power j plus k minus 1 by j plus k minus 1. So, this is equal to 1 by j plus k minus 1 please. So, we see that inner product of fj fk equal to like this thing. This implies that if I consider gkj, gkj equal to 1 by j plus k minus 1. See, if I compare the Hilbert matrix, see kjth entry. So, let me consider the second entry of second row, that is 1 by 3. So, g of 2 2, g of 2 2 is equal to how much? 1 by 3. Here you see g of 2 2 according to this formula 1 by 2 plus 2 minus 1, that is again 1 by 3. Okay. So, we can check that gkj is equal to like this thing. So, this implies that your capital A is nothing G matrix. Since G is invertible, so A is invertible please. So, from this we can easily show that the Hilbert matrix is invertible please. So, we will see many applications of this concept. To understand more details about the inner product, we have to basically solve the many problems which are given in the exercise, and we will see that many interesting problems can be handled with the help of inner product. I will continue more on this topic in our coming lectures also.